Okay, this is our last lesson for Unit 6 over independent and dependent events. Go ahead and get your DLO down. Pause if you need to do that. And let's go ahead and try our warm-up. Pause if you need a little bit more time to try this out. And let's go over the answer now. So, we are trying to find the probability that Shelly's pin will be exactly 1, 2, 3, 4. First, we need to find the sample space of these 4-digit pin codes based on the rules described in the question. The first digit is going to be 0 or 1, which means there are only 2 possible outcomes for the first digit, 0 or 1. The remaining digits are going to be 2 through 9, and no number may be used more than once. So, for the second digit in the code, there are 8 possibilities. 2, 3, 4, 5, 6, 7, 8, or 9. That's 8 possible digits. But since none of them can be repeated, for the third digit, there are only 7 possibilities. And for the fourth one, there are only 6. We don't actually need to use any of the formulas that we learned yesterday for this one. We just need to multiply 2 times 8 times 7 times 6, which is 672. And since we want to know the probability that Shelly's pin will be 1, 2, 3, 4, there's only one combination that would be that exactly. So the correct answer is D, 1 favorable outcome out of 672 possible outcomes. So we're talking about independent and dependent events. The first thing we need to define is a compound event. A compounded event is when 2 or more simple events are happening together. First, an event can be independent, or compound events can be independent. That's if the probability of one does not affect the probability of the other. Like if you draw a card and then roll a dice, or the probability that it's going to rain on a day, and the probability that I'm going to give you a piece of candy. They don't have anything to do with each other. A dependent event, or dependent events, are events that affect each other. They affect each other's probability. For example, the probability that I use an example that mentions candy, and the probability that somebody is going to ask me for some candy. So, another example would be if I have a bag of names that I'm going to draw from, and I'm trying to find the probability that I'm going to draw one name and then another name. I'm going to change the sample space by drawing the first name. So that's going to affect the probability when I draw the second name. So that is what a dependent event is. So let's look at the formulas for these 2 types of things. When we're finding the probability of independent events, all we have to do is multiply them together. When we're finding the probability of dependent events, we multiply the probability of the first event and then the probability of the second event given that the first one has happened. So we assume that the first one has happened and then find the probability that the second one will occur. So let's look at what that would look like in some of our examples. So first, let's look at this scenario. The PE teacher puts 10 red and 8 blue marbles in a bag. If a student draws a red marble, the student's going to play basketball. If they draw a blue marble, they're going to practice long jump. Josh draws a marble. He doesn't like what the outcome is. He puts it back and draws a second time. We're going to find the probability that on each draw his marble is blue. So first we need to know our sample space. Well, there's 10 red and 8 blue, so our sample space is 18. There's 18 possible outcomes here. What makes these events independent? The fact that he puts it back. Since he puts the marble back, the sample space doesn't change. So we want to know what's the likelihood that the marble will be blue both times. Well, there's 8 blue marbles out of 18 possible, which reduces to 4 out of 9. To find the probability that both will be blue, we multiply them together. 4 times 9 times 4 times 9, 4 over 9 times 4 over 9 gives us 16 over 81. So the likelihood that he draws 2 marbles is 16 over 81, or about 20%. So that is how we find the probability of independent events. Let's look at the examples down below. A king is drawn from a deck of 52 cards, and then a coin is tossed and lands heads up. A lot of these questions will deal with decks of cards, and I know that not everybody plays with a standard deck of cards just in their everyday life. So if you didn't know, in a deck of cards, there are 4 what we call suites: spades, hearts, clubs, and diamonds. There are 4. And in each suite, there are 13 cards. So the likelihood of drawing a single suite is 13 out of 52. And in each suite, there's 1 of each number: 2, 3, 4, 5, 6, 7, 8, and 9, and 10. And then a couple of what we call face cards: Jack, Queen, King, and Ace. So in a deck of cards, there are 4 kings. A king is drawn, and then a coin is tossed. So we have to determine, are these independent or dependent? They are independent. The cards do not affect the coin. The probability of A, since there are 4 kings, it's 4 out of 52, which reduces to 1 out of 13. The probability of B, getting heads, is 1 out of 2. And to find the probability of both, we multiply them together, which gives us 1 over 26, 1 out of 26 to get both. Let's look at the next one. A spinner with 4 equally spaced sections numbered 1 through 4 is spun and lands on 1, and then a die is tossed and rolls a 1. Since those don't have anything to do with each other, it's independent. The probability of A, getting a 1 on the spinner, is 1 out of 4. Rolling a die and getting a 1 is 1 out of 6. A die has 6 sides, or in this case, we're assuming that they're using a 6-sided die. Independent events, we multiply together, and we get 1 out of 24. A red marble is drawn from a bag of 2 blue and 5 red marbles and not replaced, and then a second red marble is drawn. The key words here are not replaced. Since we're not putting it back, that means we're changing the sample space. That means that these events are dependent. So the probability that A will happen is 5 red marbles, that's our favorable outcome, out of 5 plus 2, 7 possible outcomes. 5 out of 7. But then we have to find the probability of B, the second red marble, given that A, the first red marble, has already been drawn. If the first red marble gets drawn, we have only 6 left, and only 4 of the 6 will be red. So we reduce our total sample space, and we reduce the number of red marbles specifically if A has already happened. That reduces to 2/3.